Hello, this is Ira again. So we're still going over the thermodynamics section of the GFEs, and we're going over the section 183 steams. So, and I'm just gonna start right on because this one has a lot of knowledges. It has a lot of information. So I'm thinking that I'm just gonna go over and explain the information that it might help us answer the questions on the GFEs. And I am, as usual, dividing this in knowledges and also putting what knowledge, the information that each knowledge contains. In this case, this knowledge is going to contain information about pressurizer. But to me, like the way that the question was being asked, I couldn't understand it until I dived a little bit into this type of pressurizers. And there's only two questions. But to me, it was very, very important, and it really helped me a lot trying to understand this. Okay, so let's start right on. So for the pressurizers, we're going to have two types of pressurizers. We're going to have a static and dynamic. So let's start with the easy one, a static pressurizer, which is going to be this one. It's a partially filled tank with a requirement of gas pressure type in a void area. In this case, we use nitrogen. So that's going to be our static, right? Then we're going to have the dynamic pressurizer. So the dynamic pressurizer is a tank in which a saturated environment is controlled using heaters to control temperature and sprays to control pressure. So this dynamic pressurizer uses controlled pressure containment to keep high temperature fluids from boiling, even when the system undergoes abnormal fluctuations or transients, right? So let's get more into detail. So the evaporation process, like for in a pot, for example, is one in which a liquid is converted into vapor. Right, we're gonna have flame here, and we have liquid is converted into vapor. That's gonna be our evaporation process. So all the molecules in the liquid, on this pot, all the molecules are gonna be in continuous motion. They're gonna be moving around, and the molecules that move most quickly are going to possess the greatest amount of energy. Makes sense. And this energy occasionally is going to escape to the surface, right? The ones that move faster escape to the surface. That makes sense. So when molecules move into the atmosphere, the molecules are going to be in this gaseous or vapor state. Liquids at a high temperature have more molecules escaping to the vapor state because the molecules can escape only at higher speeds. So if the liquid is in a closed container, the space above the liquid becomes saturated with vapor molecules, like in this picture here. Right? And this is our enclosed container. So the return of a vapor to a liquid state is what we're gonna call condensation, because that also can happen. So when the amount of molecules that condense is equal to the number of molecules that evaporate, so that means that there's this dynamic equilibrium between liquid and vapor. So here we're going to have this dynamic going on between liquid and vapor. Saturated liquid, saturated vapor. So the pressure exerted on the surface of the liquid by the vapor is called vapor pressure. And vapor pressure increases with the temperature of the liquid until it reaches its saturation pressure, at which time the liquid boils, right? So when a liquid evaporates, it loses its most energetic molecules, and the average energy per molecule is then gonna be lower, which in turn is gonna cause a reduction in the temperature of the liquid, right? So boiling is an activity that we can observe in a liquid when it changes from liquid phase to vapor phase through the addition of heat. And the term saturated liquid is used for a liquid that exists at its boiling point. For instance, water at 212 Fahrenheit in standard atmospheric pressure is an example of a saturated liquid. Saturated steam or saturated vapor is a steam at the same temperature and pressure as the water from which it was formed. It is water in the form of a saturated liquid to which the latent heat of vaporization has been added. So when heat is added to a saturated steam that is not in complete liquid, its temperature is increased and the steam is superheated. And that's also something that we're going to go over on the PS diagram and TB diagrams as well. So the temperature of the superheated steam is expressed as degrees above the saturation, and it's called degrees of superheat. And we will go over that. That's part of what we will see in the rest of this section 193.003. But we can also see this is also like part of our pressurizer. So that's why it's important going over all of this. So the pressurizer is going to provide a point in the reactor system where liquid and vapor can be maintained in equilibrium under saturated conditions for control purposes. So, and this is how we're going to control, and we will go over more information on these two topics. This is also important. This is what we're going to actually care about when we're trying to answer the question on the GFE. So a dynamic pressurizer is going to help us maintain a system pressure above its saturation point. And it's also going to provide a means of controlling the system fluid from expansion and contraction. And also it's going to help us control the system's pressure. That's why it's called a pressurizer, because it will help us to control the pressure. But when we're talking GFEs question in this part, one of the things that caught my eye was something called outsurge, because I was not aware of that word at all. I didn't know what it meant. So here we have our pressurizer. In this, we have this surge line. And this is what we're going to call either outsurge or insurge. And I will explain what each one of them means. So a decrease in the RCS average temperature is going to result in an outsurge from the pressurizer. So this line is going to be directly connected to the RCS, right? As it says, if we decrease the temperature average of the RCS, in turn, we're going to decrease our pressure, right? And that's what it's called an outsurge. Again, a decrease in the RCS average temperature will result in an outsurge from the pressurizer. As the water volume decreases, the steam bubble expands to maintain pressure. The control heater current will increase as the pressure increases. So we're going to have the heater on, right? Because we are decreasing the temperature. We're converting more saturated vapor into saturated liquid. So if we really need to maintain the same pressure in the pressurizer, we need to start turning on the heaters, right? Because we need to go back up to the same pressure that we were before. So this increase in energy to a saturated water volume will convert some of the water at the water-steam interface to steam. So now remember, the specific volume of the saturated steam is going to be greater than that of at the same temperature of the water. And that's something that we're going to use for steam tables as well. Since the steam volume expands faster than the water volume decreases, so the steam volume is going to expand faster than the water volume, the net effect is to stop the pressure decrease. So the heater is going to continue to add more energy. So it's going to get more and more energy, more energy into the water, because we want to return the pressurizer pressure to normal conditions. So as the pressure rises, then the backup heaters are going to turn on. So we have we are heating stuff in here, increasing the temperature. We reach the temperature that we needed to reach. We need to turn off the backup heaters, right? And as the pressure continues to increase, Controlled heating current will decrease because we need to stabilize the pressure, usually at 2250 psia, right? So we need to make sure that we stabilize it. So basically, just going over again, outsurge, we will get it if we get a decrease in the average temperature on the RCS because we have this surge line connected directly to the RCS. And that's basically what it is. Insurge is a little bit more complex. On an insurge, we're gonna have a increase in the RCS average temperature, which it's gonna cause this insurge into the pressurizer, and this insurge will increase the pressure by compressing the steam bubble, right? So this compression will cause some of the steam to condense, and since water has a smaller specific volume than the steam, the pressure increase should be slowing down. So we're not gonna have questions as related to insurge, only outsurge. So we just basically need to remember this part. And I think the question, it will be more related to, which pressurizer is gonna maintain the highest pressure. It's just a comparison between these two. But if the question asks, if we have an outsurge, we are obviously talking about this down. We're not talking about this one. We're talking about this pressurizer, this dynamic system, if we have an outsurge, right? So we're going to be talking about that one. And that's how we'll know, at least we can discard this other one in our questions, right? So what we know that if we talk about this one, outsurge, we're going to start seeing a decrease in the pressure because we have a decrease in the temperature. And that's actually what's going to answer our questions. We only have 2 questions, and that's key to answer those 2 questions. Now we have something related to volumetric flow rate. We're going to have a question where it's going to be asking us about calculating volumetric flow rate. We're going to be giving, I think, gallons per minute. And we're going to be giving also a specific volume. So we just need to put in the information in there to be able to get out the final volumetric flow rate. So that's why we use this formula. So now we're going to have also another section where we're going to be looking at the different points of a TS diagram. So here we're going to have this TS diagram, and different points are going to be different states of the, of the liquid. So in this point here is where we're going to have subcooled liquid. And here is the temperature, temperature is increasing. So if we increase the temperature, we're going to get to a point where we are going to start boiling, right? Remember that we discussed that we're going to start boiling, and we're going to reach to saturation. This is what we're going to call saturated liquid. Then we're going to have here a saturated mixture eventually. If we continue adding heat, we will have a saturated mixture. We're going to have a certain percentage of gas or steam and water. And then we can convert all this liquid 100% into vapor, steam, or whatever. And that's going to be this point, and it's called saturated vapor. And if we continue adding heat, there's going to be a point where we're going to superheat our vapor or steam, whatever we have in there. And that's something that we call superheated vapor. And that's how we're going to look at on our TS diagram as well. And we're also going to have our TV diagram too, because we can have instances where we have, pressure 1, pressure 2. When we're getting something like, I don't know, what's going to happen to the temperature if I decrease the pressure, right? If I decrease the pressure, what's happening to my pressure, or what is happening to, I don't know, my liquid? Am I decreasing something or increasing something here? That's kind of like the questions that we are going to get from GFEs. So we just need to be a little familiar with this type of diagram. So if I decrease the temperature or the pressure, yes, my temperature will decrease. I will have a decrease in my vapor temperature. So, but I will also have a decrease in my liquid temperature as well, right? Because this is part of a mixture, so I will be decreasing both. Then we're gonna be able to use this formula to calculate quality. To calculate the quality, if we use we're gonna be giving a certain mass for vapor over mass total. That's what's gonna give us this quality number. And quality is gonna be basically this part from here. Quality is, let's use this point, quality is equal 0 when I have saturated liquid. And this one quality is 100% because everything was already converted to steam. So I have 100% steam, right? Here I have 0% steam and here I have 100% steam. I can also use this part as well, right? My enthalpy, I can use my enthalpy to obtain the quality as well. And we can also calculate the moisture. So the moisture is gonna be kind of like the inverse of my quality. So it's gonna be 1 minus x times total. If I want to calculate, for instance, what's the mass of my liquid. So I can use my moisture, 1 minus x. And moisture is with big M. Also, we're going to take a look at some of the properties. For instance, if I'm giving temperature, the other value that I need to, be able to calculate something else is pressure. Temperature and pressure they go together. They always go together. Just remember that, and you'll be able to answer the questions. Now, then we're going to be able to use heat transfer formulas. So I suggest you to start remembering these formulas for the ones that we went to college. We definitely remember this one. It's going to be Q equal mCp delta T. Remember Q equal mCp delta T, or Q equal M delta H. And when do we use this type of formulas for heat transfer? So this one we can use it normally, but if we have a change in phase, we use the formula with the enthalpy. If we don't have a phasing change, we can use this one. So now, pressure and temperature. So remember this formula that will help us to calculate the quality. So if we're giving enthalpy, entropy, or a specific volume, doesn't matter, we will be able to calculate the quality. Again, TS diagram. Remember that we talk about these points on our TS diagram, or subcooled liquid, saturated mixture, saturated vapor, and superheated vapor. Our boiling point is going to start in here on our saturated liquid line. This is kind of like some formulas that I got from here. So if I want to calculate the amount of quality added into a system, I'll just divide the enthalpy added over the enthalpy of the fluid in the steam. Also, they're going to be able to ask me for the exam superheater or the degree of superheat. That's basically that. It's going to be only the difference between the temperature of the steam minus the saturated temperature. And they will probably give me like a pressure number or something. So for heat added, I have some of the formulas that we can use for the Mollier diagram, because we're going to use the Mollier diagram. One of the things that I can remember for this is that on some of the Mollier diagram questions, I'm going to be asked what's the turbine work, and I'll just get the difference between the enthalpy of the steam and the enthalpy of the exhaust, and I can use the Mollier diagram for that, which is this one. And also I'm going to have problems that talk about volume and specific volume. So these are the formulas that we probably need to remember. A specific heat. A specific heat is just delta H over delta T. Enthalpy, again, we see enthalpy again. We see again the formulas for heat and heat transfer. This part is going to be on your exam, this information. So we already know heat, heat transfer. We're going to get to be able to calculate the time, so we just need to kind of like work with this formula to kind of like get the time parameter from here, because in some instances they're gonna be able to ask us information about how long it takes the pool to reach a certain temperature. So then we can actually use this formula. We will be asked about mass and mass flow rate. So these are the formulas for mass and mass flow rate that we will need. And finally, I think this is going to be it. We're going to go over turbine efficiency. And this is the formula for the turbine efficiency. This is the formula for Bernoulli's. Actually, this formula, they don't have it like that, like on the example for the GFEs. This one I just memorized it. I think it's very simple. So I'm going to use another color because then, okay, so I have initial pressure times specific volume of the fluid times 144. And this one goes here below 2 minus speed to the square of the final minus speed of the square of the initial over 64.4. And I actually just memorized this one in order to solve, like if I'm giving two pressures and stuff like that, I will just be able to type in these numbers. This is going to be given, this is going to be giving this. They're going to give me the pressure temperature, but I can just go and check the specific volume in the steam table, and I'll just type everything in and I'll be able to answer the question very easily. And this is another similar formula. It's gonna be similar to this one, like the question, but they're gonna be asking us about the enthalpy. So that's actually what I did, just try to kind of like memorize it. And then finally, we're gonna go over net positive suction head. So this is the formula. Net positive suction head available is equal to the pressure of the eye minus the saturated pressure. And for instance, if they're asking us what's the height in feet for something, if they're giving us the net positive suction head available, which is multiplied by our volumetric, specific volume, times 184. And that's kind of like all the formulas that we're going to use for this section. And I'll just go over a couple of the problem examples next. Right, so we know now that we're going to have for GFEs, usually we're going to have only two problems that are going to be asking about outsurge. So let's take a look at this question. This is the first question on the question bank from May 2020, question P1774. So it says two identical pressurizers are connected to the same location on two identical reactor coolant systems operating at 1000 psia, right? The pressurizers need to have some pressure, right? Hence the name pressurizers. This pressure can be different, right? It can be all the way to 2250 psia. So this is not like super important in this part. So now it's telling us pressurizer A. Okay, so it's giving us two pressurizer A, pressurizer B. Pressurizer A contains a 50% saturated water and 50% saturated steam. What does this look like? This pressurizer A looks like a dynamic system, right? That's what it looks like. Remember that? We're gonna have saturated water and saturated vapor and water. And then we have pressurizer B. Volume contains 50% subcooled water at a whatever, doesn't matter the temperature, and 50% nitrogen. What does this pressurizer look like, right? This pressurizer is like the other one, right? So we have one saturator, we have one subcooled, so we are going to have these two types of pressurizers. But what the question is asking, so we know we have these two different types of pressurizers, so this is asking which pressurizer will maintain the higher pressure following a sudden 10% liquid outsurge from each pressurizer and why. So when we talk about this, we can have an outsurge in any of them, but since we're already talking about a pressurizer in our reactor cooling system, we are not going to have a pressurizer on a reactor cooling system that contains this nitrogen blanket, right? So we have here this dynamic pressurizer, and we're going to have this static pressurizer here. So this is the type of pressurizer that we are going to have on our reactor cooling system. This line is connected directly to the reactor cooling system, right? And we already talked about the outsurge or insurge happening here. So because of that, I already know that I'm going to eliminate my static pressurizer, which is going to be pressurizer B. So I'm like, this one is just not going to be part of it. I'm not going to even consider it. But then I have two options here, two answers. The first one, it says, pressurizer A, due to vaporizing of saturated water as pressure begins to decrease. What is happening? Do you guys remember what we talked about in this one? And if not, so when we have an outsurge, basically we have a decrease in temperature on the reactor coolant system. The temperature average of the reactor coolant system is going to decrease. So that's one of the things that is happening. And that's going to create having a decrease in pressure. We have a decrease in temperature. That creates a decrease in pressure, and that gives us an outsurge. That's the definition of the outsurge, right? So pressure begins to decrease. That seems accurate to me. And because of that, yes, we have evaporating of saturated water as the pressure begins to decrease. So to me, this seems like an answer that I need to consider. But then let's take a look at the other one. It says pressurizer A, due to the expansion characteristics of saturated steam being better than the expansion characteristics of hydrogen. One of the things that we need to consider when we have a dynamic system. When we have a dynamic system and we're going to have this pressure change, we're going to have a flashing from water to steam. This flashing from water to steam is going to help mitigate this is important in a dynamic system, that helps mitigate the pressure drop. So the pressure drop is not going to be, as I don't know, like this one, right? Because here we are, this flash into steam is going to help mitigate. And that happens in a dynamic system here. So this doesn't happen in a static system, right? So the pressure is going to drop. I mean, you just have to use the the PV over this formula, PV over T formula, and that's like basically like the formula that you use to kind of like determine, like using the ideal gas law to determine, it's just a straightforward pressure decrease. It's just basically linear. It's not like in here in the dynamic system, right? The pressure is not gonna, it's gonna have a way of being mitigated in this part. So because of that, because we have the vaporization of some of the saturated water to steam, we're helping mitigating this pressure drop. So again, the question is asking which pressurizer will maintain the higher pressure. Which one is going to maintain the highest pressure? So if I start with the pressure of, it doesn't matter the pressure that I start with. So this one, it gives us an example of 1000 psia. This one is giving us an example of 1000 psia. If I use ideal gas law in this one, and they give you the example on how much that would be, right? Because you have the 10% outsurge, right? They're giving you the 10% outsurge. So we are talking that because of that, it's going to go down 910 psia because of the 10% outsurge. So now, this other one, this flash to steam, is mitigating. Because it's a dynamic system, it's not something like I can just calculate like very easily, but I can deduce because of this, right, that I'm not going to go directly 10% below. It's going to be lower than 10%. So this is going to have the highest, right? This is going to give me the highest pressure, or this is the one that will maintain the highest pressure during the outsurge in here. I hope this helps on this one. And the other one is basically the same. It's just basically the same. It's just changing, it's just telling you the pressurizer A. See, pressurizer A is the static system, and the pressurizer B is the dynamic system, right? And you know how to do that. And that's only 2 questions. But okay, let's move on to the next one. The next one, it's very, very simple. And I think there's only one question from that one. So this one, it's question P3874. We have a reactor operating normally at 100%. That is like blah to me. It's just something, I have a reactor. Everything is going to be connected to the reactor, right? So I don't want to complicate things. To me, like everything is connected to the reactor. So don't confuse yourself or don't get overwhelmed for all the words that you're going to find. So now he's talking about reactor coolant entering the reactor vessel. So we have reactor coolant. This might be important. Reactor coolant enters. What is this? It's going to be in liquid form, right? This is something important to consider later. Enters the reactor vessel at a temperature of 556 Fahrenheit and total flow rate 320,000 gallons per minute. The reactor coolant leaves the reactor vessel at 612 Fahrenheit. I highlighted the important stuff. Maybe I should highlight this one as well. Okay, well, the question is asking, what is the approximate flow rate? So I need to know the flow rate of the reactor coolant leaving the reactor vessel. So when we're trying to calculate that, we need to determine what comes in, comes out in terms of flow, right? What's going to come in, it has to come out unless there's a leak. If I have something else, if what I get out is different, there's something different in my system. There's something going on, something else going on. So, okay. So what is the formula for flow rate? Flow rate is gonna be equal to my volumetric flow rate times my density, which is gonna be equal to my volumetric flow rate over my specific volume, right? And that's important because they're giving me temperatures, right? They're giving me temperatures, and I know that I'm dealing with a liquid, so I know that that I have to use a specific volume, right? Because I can get a specific volume from saturated liquid at these temperatures, right? Because the steam table doesn't give me this. The steam table give me this information. So that's what we're gonna use. We're gonna use the steam tables and we're gonna use this formula, right? So this is telling me, okay, this is when it comes in, this is when it comes out, and this is my flow rate. What is my new flow rate, right? So we establish this equality. What comes in is what comes out, right? What am I being given? I'm giving the temperature at which the flow comes in, temperature at which the flow comes out, and my initial volumetric flow rate. Now I need to calculate this other one here. Okay? And then I set it up in here, accommodate everything, but I don't know my specific volume for this, so I need to go to my steam table. And the steam table that I have here is a little different, but it's gonna be fairly similar. So the first one that is asking, so it's asking me for 556 and 612. Let's try to find it. 556, 556. This is close to 556. And 612. So this is my specific volume, right? This is how I'm gonna go to my steam tables and look for it, right? Using temperature, I go to the saturated liquid part and then I get my information. Once I get my information, since here I don't have it exactly, but if I go to my steam table, the one that I'm giving for GFEs, I'm gonna be giving a steam table specifically for this, I will get the exact numbers. In this case, I will have to do an interpolation. So, and this is the information that I will get. So for my volumetric, my specific volume at 556 is 0.02195, and at 612 is 0.02422. And I'm getting a volumetric flow rate of 353,000 gallons per minute. So I just looked that up here. And this is my answer, delta. That's how we do this one. Okay, so now let's go and do the next one. Okay, so for these ones, now we're gonna have different tables, or we're gonna have different graphs in here, right? So this is gonna be important because this is where we're gonna start looking at this type of graphs. How do I know the difference though? Because I'm gonna have the one graph that shows me temperature over entropy. I'm gonna have another graph that is gonna show me temperature and not over, but temperature and enthalpy and also temperature in a specific volume, right? So what's going to be the difference on this ones? And I'm just going to write it in here, what the difference are, right? So if I have a TS diagram for entropy, that's going to be for when pressure is constant or when we're talking about atmospheric pressure. And also when heat is added, okay? So we're going to have a TH diagram for enthalpy. And when do I use that? I use this ones basically to calculate quality. And then I'm going to have another one, TV diagram, and that is for a specific volume. When do I use this one? I use this one if I have a change in pressure or if I have, I don't know, a quality mixture. And we will go over each one of them, but I just wanted to give a heads up on this so we kind of know the difference, right? Okay, so now let's go over and check out this question. So this question is P674. A liquid is saturated with 0% liquid. When we say that a liquid is saturated with 0% liquid, that means that we are in this part of the graph, right? We have a quality of 0%. We are completely liquid, but we are saturated, so we're going to be here. This is the saturated part. So assuming pressure remains constant, this is the pressure line. So this is my pressure line. Pressure remains constant, the addition of a small amount of heat. So if I add a tiny bit of heat, right, I'm going to move in that direction. What's going to happen if I move in that direction? Like if I add heat, I cannot move above. That's changing my pressure, right? So I'm still having the same temperature, right? So if I have a little bit of heat, what's going to happen? So at this part, right, I'm going to have a little bit of liquid vaporizing. Just a little bit because I'm changing the quality, right? So if my quality was 0, I add a little heat, I'm increasing my quality towards that direction. So let's see, yeah, will result in some of the liquid vaporizing. So, and that's why this is the right answer. Subcool liquid will be here and we are not going towards this direction. Is that will be like if we remove heat. If I'm here and if I remove heat, maybe I can have subcool liquid, right? So raise the steady state liquid temperature above the boiling point. I mean, that will be different, or like if it results in superheated liquid, I'll have to go this way, right? So that's why Charlie is going to be the answer for this one. Okay, next one is, and check this one because this one's I'm basically changing my diagram. Now I have a TV diagram. Temperature in a specific volume. Okay, this is question P774. So we have a pressurizer is operating in a saturated condition at 636 Fahrenheit. If a sudden 10% liquid outsurge occurs, what's going to happen to the pressurizer? Pressure and the pressurizer temperature. So we have to remember, right? Pressurizer pressure and pressurizer temperature. right? I hope we can remember that part because that's an important part. So when we have an outsurge, the reason we have an outsurge is because we have a decrease in the average temperature on the RCS, and that decreases the pressure on the pressurizer, right? So that's the basic concept of the outsurge. An insurge will be the opposite. But this one is asking about the outsurge, right? So now, what's gonna happen? We already have the answer here, right? Because we know what happens in an outsurge. Pressurized pressure will decrease, pressurized temperature will decrease. So it's Charlie, as long as I know what happens in a pressurized or outsurge, like I already have my answer there. I don't need to search for anything else. Okay, so, and we can see it in here in the TV diagram. So we talk about a TV diagram. We use it when we have a change in pressure. In this case, an outsurge is going to give me a change in pressure, right? I start at this pressure, I have an outsurge, I have a decrease in my pressure, so it goes down, right? So that's why I can use this diagram here. Okay, next one is another TV diagram. So this one is P874. So consider a saturated steam water mixture with a quality of 99%. So it's telling me that I have a quality of 99%. So I'm here. If pressure remains constant, so it's telling me the pressure is going to stay here. So pressure is going to remain constant. And heat is removed from the mixture. So I'm removing heat. So which direction am I going? Here, I'm going this direction because I'm removing heat. In this case, because I'm here in the saturated part and I'm starting to remove heat, the temperature of the mixture, it remains. It remains the same. But what's going to happen with the quality of the mixture? Obviously, if I remove heat, I'm decreasing the quality of the mixture, right? So therefore, my answer is D, delta. Okay, next one. It's P1075. P1075, a nuclear power plant is shut down with the pressurizer in a saturated condition as follows. So I have this pressure and temperature. Well, this pressure and temperature. So if the pressurizer is vented until pressure equals 1200, so I start with this pressure here, and then I ended up with this other pressure. What's gonna happen? I'm decreasing my pressure, right? So what's also happening to the temperature? My temperature started here at 588. So now my temperature goes down as well, right? So is pressurizer pressure liquid temperature is not going to increase, right? Because we know that it's going down. So it's not increasing. I can get rid of those ones, right? So what happens on an outsurge? Remember the first question of the pressurizer, right? We have evaporation of the liquid. That's very important when we're talking about outsurge, when we have a decrease in pressure and decrease in temperature, right? So that's what's gonna happen. So my answer is gonna be delta in this case. And that's in the first question that we saw earlier. as well. We can relate to that. Okay, the next one is question P1174. Question P1174. It's which one of the following describes saturated water at atmospheric pressure? Saturated water at atmospheric pressure. If the water is saturated, but it's still liquid, right? My quality, so I'm gonna be here. I'm saturated, but I'm still liquid. It doesn't say mixture. It doesn't say saturated vapor. If we will say saturated vapor, right? Maybe we'll say we are 100%. If it says saturated mix, that means we are somewhere in this range. But it says saturated water, right? Meaning we are in this point. This point is the boiling point. Okay? So this is gonna be my answer. Quality at 100%, this is saturated vapor. Below the boiling point, we're gonna be somewhere in there. So that's why we know this is the answer. Okay, next one, it's P1374. So we have a steam water mixture. Okay, we have a steam water mixture, so we have something in here. So it's initially saturated with quality of 95%, so I'm here 95%. So when a small amount of heat is added, so I'm adding heat, that means that I'm going towards that direction. If the mixture remains saturated, so the mixture remains saturated, and the pressure remains constant, right? I'm not changing my pressure is still the same. The temperature of the mixture what's going to happen to the temperature of the mixture? So I'm still saturated, right? Meaning that I'm still in this area. So my temperature obviously is going to remain the same, right? It's going to remain the same. But what's happening with the quality? Since I'm adding heat, I'm increasing the quality, right? So the quality of the mixture is going to increase because I'm increasing. Yes, I'm adding some heat, right? So therefore, my answer is going to be delta. Okay, the next one, it's P1474. This one says, an open container holds 1 pound of saturated water at standard atmospheric pressure. The addition of 1 BTU to the water so what's going to happen? It says, okay, you have a container of saturated water. Okay, so where am I? So I'm here, I'm saturated water, right? That's where I'm at. It doesn't matter how much I have, where I have it. It can be a container. It can be anything, right? I have the water here. Okay, but where am I in this diagram? I'm there. It can be 1 pound, 2 pounds, it can be anything. So I'm adding 1 BTU to the water. So I'm adding heat. I'm adding heat to the water. So what's happening? And we already talked about this. I add heat, right? I start vaporizing if I'm in a saturated condition, right? Because I starting having some vapor or some water turning into vapor, right? I'm changing the quality of the mixture. So therefore, Bravo is the answer. Okay, so the next one, it's P1574. So again, consider a saturated water mixture with a quality of 79%. So it's telling me, okay, you have a quality of 79%. So I'm gonna be kind of like around here. If pressure remains constant, pressure stays there, and heat is added. So I'm adding heat, I'm going towards that direction. So since I'm saturated, the temperature is going to remain the same, right? But what's happening to the quality? Since I'm adding heat, I'm increasing the quality. Therefore, Charlie is my answer. I mean, I think these ones are pretty simple to solve, right? I mean, we can go through all of them, we can use all of that, and it's going to be very simple. But now let's take a look at this one. This one is a little different because all the other ones are just going to be basically the same, right? But let's take a look at this one. This one is a little different. So we're going to use the Moulier diagram. This one, question P274. Consider a saturated steam water mixture at 500. Okay, so I have a saturated water mixture, 500, quality 90%. If the pressure of the mixture is decreased, pressure is decreased with no heat or gain loss. The temperature of the mixture will, and the quality of the mixture will. So what's going to happen? Okay, this is kind of like giving us like an option type of thing. So we need to kind of like go over and see, okay, what's going to happen. We can also try to read a diagram as well. Okay, so we have the temperature is 500. Okay, we are at 90% quality, and we have the pressure remains constant. So, well, the pressure decreases, right? We have a decrease in pressure. So what's gonna happen? Okay, now if we want to calculate the quality, right? So if we are removing heat from this mixture, so we have this mixture here, and we are trying to remove some heat, we are turning some of the vapor into liquid. That's what's happening, right? Since we are turning some of the vapor into liquid, we are decreasing the vapor part. But here, this is like a balance. So we decrease the vapor, but we increase the liquid. So basically, this one stays the same, the total mass, right? But this is only to kind of like consider like the amount of mass of vapor and liquid. And this is the formula. So it's quality equals to mass of the vapor over the total mass. So this is what's happening. So what's happening with the quality? So that means the quality is decreasing. So and it's asking what's going to happen with the quality of the mixture. So I can say that the quality of the mixture is decreasing. Just because of that, I can do that assumption or work towards that problem and say, okay, at least for the quality, I know what's happening right away. So now It's asking me about the temperature of the mixture, right? What's happening to the temperature of the mixture? So, okay, so and that's kind of like the assumption for the if the pressure of the mixture is decreased. Okay, so this one is not doing that. In this case, it's not doing this. But we can use this assumption. This can be one of the things that we can use. But for this case, we have to use something different, right? Because it's not giving us the right answer. So what are we going to do? We're going to use the Mollier diagram here. So we said that we have a temperature of 500 Fahrenheit, right? So this is a temperature of 500 Fahrenheit, and that's 680 psia. Where am I? This is where I'm at. This is my pressure here, 680 something, around here, right? And then I say that I'm at 90% quality. This is my quality line. So I got my quality line there. So how am I gonna know, if I'm doing this correctly? So I know that the pressure of the mixture is decreased. That's something that I know. So in my Mollier diagram, this is the direction where I'm lowering my pressure. So what happens when I lower my pressure on the Mollier diagram? If I start here, if I lower my pressure, that means that I start with this quality. I'm increasing my quality. If I'm going towards that direction, you can see I start here at 90. Then if I decrease the pressure, I go to 90.92, 0.94, 96. So what's happening to my quality? I'm increasing my quality, okay? So then I can say, okay, for at least for my quality, I know that if I use my Mollier diagram and I use it correctly, the quality of the mixture is gonna increase, right? So now the quality of the mixture is increasing. So that's correct. The quality of the mixture is increasing. The quality of the mixture is increasing. The quality of the mixture does not decrease. But then it's asking me about the temperature of the mixture. So if it's telling me here that I decrease my pressure, it's going to happen to my temperature, right? Pressure 1, pressure 2. I'm decreasing my temperature as well. And I can see it in this diagram here very easily, right? So on this one, my answer is going to be Bravo. So for this one, I can use this and I can use my Mollier diagram to kind of like determine that. And the Mollier diagram, if we know how to use it, is going to be very helpful. There's going to be another problem where we can only use this part, but this is not the problem, where we're going to only use this one here. Okay, because it's asking us, it's telling us the pressure of the mixture is decreased. So we have a change in the pressure. It would have been different if it will tell us that the question will ask about a saturated mixture that remains in a saturated condition. We can use this part. Okay. Now, this is another similar question that we already seen. This is something similar. We have seen something like this already. So all of these are going to be these PVTV diagrams, right? All of these ones. So these are going to be basically the same. But let's take a look at this one. This is going to be important. We need to know the names, right, of each step on my TS diagram. Okay, question P574. So it doesn't matter like what the question asks, but for instance, I have my TS diagram here. And this part is where I have my subcooled liquid. If I'm increasing the temperature, I'm adding heat. I'm gonna came to a saturated condition. This is saturated liquid. This is my boiling point. Then this line is gonna be my saturated mixture part. This is where my quality is gonna change from 0 to 100. This is my saturated vapor point. And then here is gonna be superheated vapor. So that's what I'm gonna start having there. Okay, so now let's take a look at question. Let's see what question we haven't seen yet. Question P1976. P1976. Okay, this question. For question P1976, we're gonna use a formula. What the question is asking us. So, which one of the following is the approximate quality of a saturated steam mixture? So it's asking us about the quality. We need to calculate X. What's this? We're somewhere in here, but where exactly? They're giving us temperature of the saturated steam water mixture, and they're giving us the enthalpy. So we already have some information. So what is the formula? For this one, we're going to use this formula. We're going to use the enthalpy that we are giving. It's equal to the enthalpy of the fluid plus the quality times the enthalpy of the fluid and the mixture. I mean, this is the mixture. So what we're going to do is we're going to go to our steam table, right? We're going to go to our steam table and let me make this bigger. We're going to go to our steam table and we're going to get HF at 467. And we're going to get HFE at 467. And if we know how to get that correctly, so that's going to be 449 BTU over pound mass. And this one is going to be 756 BTU over pound mass, okay? So now we just need to substitute in here. So what we're trying to get is this one. So we need to, calculate or recalculate. So I can say my new formula is this. So I have my HX minus HF over HFE, and substituting all the values, I'm gonna get approximately 0.73. And if I turn that into percent, that will be 73%. And that's the formula that I'm gonna use for that. So now let's take a look at another question that is slightly different. It's gonna be question P3375. Okay, P3375. Where are you? Here. Okay, P3375. Is that the one? No, that's not the one. Oh, because it's here. See, it's here. Okay, question P3375. This one, we have a saturated mixture with an inlet quality of 60% that is flowing through a moisture separator. The moisture separator is 100% efficient for removing moisture. How much moisture will be removed? So the question is talking about moisture. What is moisture? How do we understand moisture being removed? Right? So it's getting rid of all the liquid that we're going to have. So if we want to get rid of the moisture, we have to increase or heat at it. We have to go towards that direction if we want to remove all the moisture. So we have to get closer, right? So to 100%. So and we start with 50 pounds of mass. So we're giving mass. We're giving a quality here, 60%. So now what formula can I use? So it says how much moisture will be removed by the moisture separator from 50 pounds of the steam water mixture. So we have M mass total is 50 pounds. My quality that I'm starting with is 60% or 0.6, right? And I can use this formula. Mass of the liquid being equal to 1 minus X times total mass, right? Because I need to know, okay, this is basically saying, okay, this is my 100% minus my 60%, right? Because I'm already 60% quality, but I'm trying to see how far I am from my 100%. So in this case, I know that I am 40% far. That's the rest, right? Because if I'm 60% here, so I still have another 40% in order for me to remove all the moisture. And the total mass is 50 pounds. That's gonna give me 20 pounds. So, and that's basically the amount of liquid that I need to convert to steam to reach my 100%. And the answer is bravo. Yeah, slightly different question. There's gonna be questions like that. I think so. Let's see if we have something different. Yes, now we're gonna have another question. It is gonna be slightly different. So this question is gonna be question P7039. P7039. And this is gonna be like, oh, this is like a little bit more complex. Not really. Just has a little bit more steps. Nothing that we don't remember from thermal at school. Okay, so this one, it's P7039. Okay, given the following initial conditions for a spent fuel pool. He's giving me the spent fuel decay heat rate. So I have a heat rate. My heat rate is going to be Q dot. So I have my heat rate in megawatt. Then it's giving me the temperature of the spent fuel pool water. Then I have the mass. And then I have my specific heat. So remember my formula, QMCP delta T. My M is a rate. So I know I can do mass over time. And this one, I can just turn it into that because here it's just giving me the mass part of it, right? So I can turn that into this, and then everything stays the same. Okay? And then I know, okay, then I need to go and see, okay, what is this asking for? So if a complete loss of spent fuel pool occurs, how long it will take for spent fuel pool water temperature to reach this temperature? If anything happens, I don't care what happens, how long is it going to take for the spent fuel pool water to reach this temperature? Anything can happen. It can be complete loss of spent fuel pool, it can be anything. So I need to calculate for time here. So I just need to take time out, put my heat rate in, and do the calculation, but I need this in BTU per hour, right? I calculate also my delta T. I get this one, and I already have this two. So it's just a matter of plug everything in, and my answer will be 17.94 hours, which is approximately 18 hours. And that's going to be my answer for that. Very simple, very straightforward. It's asking for the time, right? This is how we get the time. Now, there's going to be another problem. It's going to be P6939, I think. P6939. Okay, for P6939, we need to do something different here. In this one, we have a nuclear power plant experienced a loss of AC electrical power due to a natural disaster. Blah. To me, that's blah. It's trying to make me feel scared of the question. Anything can happen. Then the second paragraph, or the second line. A few days later, there is a turbulent boiling throughout the entire spent fuel pool. Okay, something got heated. Something is changing in there. So average spent fuel assembly temperature is elevated but stable. Okay, yeah, makes sense. Yeah, you have turbulent boiling, so there's some boiling, some increase in temperature. Nothing that scares me from this part. Now, assume that the spent fuel pool contains pure water in thermal equilibrium. So I only have water here. And that boiling is the only means of heat removal from the spent fuel pool. Okay, let's analyze that. So now, what am I being given here? This. Current conditions. They're giving me the heat rate. They're giving me the building pressure. That's all I get. If that's all I get, how am I going to calculate Q, M, CP, delta T? I only have the pressure. No fear, since I only have the pressure and boiling is the only method of heat removal, the only thing that I need to do is go to my steam table and I can use this formula. I can use my enthalpy because I'm just only giving the pressure. So I'm giving the pressure of the liquid and I'm giving the pressure, I'm just giving the pressure. So I can get the enthalpy for the liquid and the enthalpy for vapor. because it says boiling is the only means for heat removal. So I can gather both, right? What do I need? What is this question asking me? So it's asking me about the rate, the approximate rate. So at what approximate rate is the mass of the water of the spent fuel decreasing? So how much water am I losing through this boiling, through this evaporation on the spent fuel pool, right? So that's all I need to calculate. And since I'm only giving this, I know that I can use this formula. I can use the enthalpy. So I look the enthalpy at this temperature for liquid and vapor. And these are my numbers here. I just typed that in. And this is given basically, I just need to convert my 4.8 megawatts to BTU per hour. I plug it in, and the answer that I get is around 17,000. And the closest answer to that is going to be delta. So that's kind of like how I get that answer for that. Now, there's going to be a few questions. They're going to be a little weird, a little different. So let's go over those ones. They're not complicated, or they don't have like a lot of information on it. But okay, let's go over. So the next one, it's going to be P3074. Okay, P3074. This one. So this one is, okay, the temperature is giving me the temperature, right? So the temperature of a saturated water mixture is black. It can be any temperature. Which one of the following parameter values, when paired with temperature, provides insufficient information to determine the quality of the mixture? So if I want to get the quality of the mixture, I'm going to have different formulas. I can use enthalpy, right? I can use entropy. It's going to be basically the same. Oops. Or I can use specific volume. All those formulas, they give me this, right? So if they give me the temperature and they give me the enthalpy, the entropy of the specific volume, I can get quality. So from all of this, I can get quality. But if you only give me temperature, pressure is basically the same, because if you take a look at the steam tables, if you get a temperature, you're going to get a saturated pressure, and that by itself is not going to give you the quality of the mixture, right? It's not enough information. So that's what basically this answer is going to ask you. And there's another question similar. I mean, there are going to be questions similar to that, but as long as we know this concept, like, we are okay. And then we're going to have different questions related to, asking about the percentage of saturated vapor or saturated mixture. So let's go over one of them. I just don't want to go over all of the questions, because then this video is going to take forever. It's already taking forever. Okay, 4839. Okay, this one. So, question P4839. An open vessel contains 1 pound mass of water at 204 Fahrenheit and a standard atmospheric pressure. If 16 BTU of heat is added to the water temperature will rise by about, and approximately a certain percentage of the water will become steam. Okay. we have different things going on here. So we have a container with an X amount of mass with a water on 204 Fahrenheit and standard atmospheric pressure. And then it's telling us if we add 16 BTU of heat, what's going to happen to the water temperature. We know it's going to rise, but by how much? And what percentage of the water will become steam? Okay, let's analyze this. So we know that we are giving a standard atmospheric pressure. Standard atmospheric pressure, that's going to be 14.7 psia. And the temperature, the saturation temperature for that is 212 Fahrenheit. And I think we should just have this memorized by now. Okay, so now I'm going to just draw my TS diagram. Just going to draw it here. Okay, so this is my pressure, right? This is my 212 Fahrenheit, but it's telling me that the water is at a temperature of 12.4, so meaning that I'm somewhere in here, right? So I'm gonna be below that. This is where I'm starting at. So I'm starting like somewhere around here. So this one is making the assumption that we need to assume this. We need to assume that if I want to heat 1 pound of water, it's going to take 1 Fahrenheit at atmospheric pressure. It has to be at this pressure. And that's going to be the assumption here. So if I'm heating 16, so if I want to get from 204 to 12, so the difference is 8 Fahrenheit. So I'm here basically just using 8 Fahrenheit to go from here to become saturated, right? But I still have another 8 because in total I'm using 16 BTU. But now if I add another 8 here, another 8 BTU of heat, I just need to know like by how much I am increasing the temperature, by how many degrees, right? So for that, I can use this formula. Or remember that we have this other formula. So we have this set of formulas here. That we could use. So I know that the water temperature is going to rise about 8, right? That's the first thing that I already calculated. So that's my first calculation there. So the water temperature rises by that. I already have that one. So now I need to go to my steam table again because I need to know what's gonna be my kind of like the final. So I'm gonna start with some amount of BTU here and BTU here, right? So if I go to my steam table at 14.7 psia, so let's just go over that. That's gonna be on page. Let me see the page because I'm actually going. Okay. So if we go to page 11 from our steam tables, saturated liquid. Oops, I wanted to erase this. So my HF is where I start. It's gonna be 180.13, right? That's where I'm starting here. 180.13 BTU over pound mass, right? That's where I'm starting. But if I'm adding another 8, right? So that's gonna increase. So I'm gonna have an increase of 188.13 BTU pound mass. And that's where I'm gonna move in here. That's where I'm gonna be at 188.13. Because that's the amount that I'm increasing, but in percentage, how much that's gonna be. And in order to calculate that, that's why I need to use this other formula. Okay, so now what's my HFG? My HFG is gonna be 970 BTU over pound mass, right? So and if I do all my calculations correctly, to calculate my quality, that's gonna give me about 1%, right? So this is where I'm gonna be at. And you can see up the numbers, right? So if I'm 180 here, I increase to 188, but here I'm 9, or here my HFE is 970. Also, what's my HG is 1150. So I know that it's gonna be around 1%, right? It's like very, very minimal the increase in percentage because I'm only increasing 8 BTU. If I wanted it to increase to 10%, I'll have to add like 115, more than 115 BTU to make it 10%, right? So, and this is kind of like how we solve for this one. I know it took me longer to go over and explain this, but you need to use the steam table on this one. And see if there are some other questions. There are going to be questions that are going to be similar. I think there's just one. It's going to be similar to that one. Everything else, I think it's pretty straightforward to solve. You're going to have questions about heat added, and you're going to have questions about the Mollier diagram. So make sure that you learn all the questions about Mollier diagram because I cannot show like all the questions of the Mollier diagram here. I'm just trying to look if there are some other questions that might be a little bit more difficult, but I don't see anything overly complicated. Everything is gonna be pretty similar. But there's another question that might be a little, or that you might need to add an extra step. So let me just go over that. So it's gonna be P4139. P4139. Okay, it's this one. This one might require an extra step. So the question P4139, a saturated steam water mixture at 50% quality. Oh, this looks terrible. 50% quality is leaving the main turbine at this rate, and it's entering the condenser at this. And it's giving me the temperature of the condensate hot well. I know that for the first time this is gonna be complex because you need to understand how stuff is working. So you're gonna have your turbine, you're gonna have your condenser, this is circ water, and then you're gonna have the hot well. So we have main turbine. So what comes in comes out, right? So this is the flow rate, what comes in comes out. Then we know that the condensate enters the hot well. So this is where the hot well starts at 112. And it's telling us that it's entering the condenser, meaning that it's exiting the turbine at 1.6 psi, right? So this one goes here, and this one, basically this is inlet, this is outlet, right? Okay, so what's happening? So in the condenser, we're gonna have this circ water that is gonna start cooling some of the vapor entering into the condenser, and the hot well is gonna collect all that water in there, right? So what do we have? So we have a change in phase, right? From this one has to be high quality vapor, and when we get here, we have liquid, okay? So if we have a phase change, what formula do we use? If this is asking for which one of the following is the approximate condenser heat transfer rate, BTU per hour. What is that? BTU per hour is my heat transfer rate, my Q. But since it's telling me that I have a situation when I have a phase change, I have to use my enthalpy, right? But okay, there's another extra step here. I cannot just go directly and use this part. Why? Because it's telling me that I have a saturated steam water mixture here, right? So what do I have to do first? I need to determine my enthalpy. So that one is easy. So remember this one. So I'm giving the quality. Oops, I deleted. Okay. I'm giving this quality, right? I know that this one is at 50%. So which one should I use? Because it's giving me this information. And I might get confused on this one because I'm like, okay, do I use this part or do I use this one, right? In this case, what I have to use is what's entering in here because this is the part that is telling me that, you know, it's 50% quality, leaving main turbine and entering main condenser, right? So this is attached to it. So I'm gonna use this one. So what I'm gonna do is I'm gonna go to my steam tables, right? To calculate my HX. So I'm gonna go to my steam table and grab the information on this one at 1.6 psia and this one at 1.6 psia, and I know this one is 0.5 because it's at 50%. So my answer will be about 600 BTU per pound mass. Okay, so that's my answer. So that's what's coming in, right? This is what's coming into my condenser. In condenser, right? So now I have another. I have to get my H out as well. Okay, so now for H out. So H out, we know that what enters on the condensate hot wall is what's exiting the condenser, right? So that's gonna be our H out. So we have to go and take a look at the steam table at 112 Fahrenheit, and we're gonna use the one that is for water, for fluid. So that's gonna be like around 8 BTU over pound mass. So we have our formula. Heat transfer rate equals mass flow rate over or times H in minus H out, and we already have like all that information there. So we just need to plug everything in, and we will get something around 5.2 times 10 to the 8 BTU per hour. But that's basically how we get each one of them, and it sometimes it gets a little bit confusing, but this is what's coming in, this is what's coming out. And in this step, since we're giving the 50% quality, we just initially need to use this formula first, okay? So that's kind of like one of the problems that has an extra step on it. I think there's gonna be another that is telling, okay, if I have a quality of 30%, so what's gonna happen? So we just use the same approach as this one. So now there's another problem that is a little bit different. It's simple, but it's different. Let's take a look. It's, I think, okay, P3575. Is it this one? Okay, yes. This is one of the last items that we will see in here. Okay, so for this one, okay, my dog is here. Don't make a noise so he doesn't bother us. Okay, so now P3575, the question is, okay, the following steady state 100% power condition existed just prior to a plant shutdown for maintenance. So initially we have this, right? We have that. So now these are the conditions for the plant that we had. So it says that then during the shutdown, 5% of the total steam generator tubes were plugged. So if 5% of the total steam generator tubes were plugged, that means that 95% of the steam generator was functional, right? So, and we need a steam generator to create like this. This is the one that dictates, how much steam we send to the turbine, how much energy we generate. So this is kind of like dictating like or heat transfer, right? So this is the one that is dictating or heat transfer here. Okay, but let's continue with the question. So it says, which one of the following will be the approximate steam generator pressure when the plant is returned to 100% power? Okay, so it's asking about the steam generator pressure. Okay, but we were talking about, okay, the steam generator kind of like dictates the heat transfer rate. So if we have this heat transfer rate before, is going to be basically equal to the after. But in this case, we had a slight change here because we have during the shutdown, right? So this is the information before shutdown, and this is after shutdown. We have only 95% of the steam generators functional. In order to calculate this, so we know that Q equal to this formula, overall heat transfer rate, right? This is my overall heat transfer. That's what I'm trying to get. So since I know delta T, this is before, is going to be equal. So now the after. So the after is going to be different because in the after I only have 95% of my steam generator tubes were functional. So I was only providing 95% power basically, or heat transfer. Okay. But everything remains the same. It says that the mass flow rate and the RC is temperature average, everything is the same. So that means that I can get rid of that. So I have my delta T before equal to 0.95% delta T after. But what's my delta T? Okay, so my delta T is going to be equal to my temperature average before minus the temperature of my steam generator. So let's do this more simple. So delta T is going to be equal to my temperature average minus the temperature of the steam generator. And that's going to apply to both sides, okay? To my before and to my after. Okay, so now I'm going to apply that to both sides of the equation. So I'm going to have my temperature average before minus my temperature, the steam generator before. That's going to be equal to my 0.95 temperature average after minus temperature steam generator after. But this is asking about the temperature, like the pressure of the steam generator. But if I get the temperature, I can get my pressure, right? So basically, I need to solve for this for this guy here. That's what I need to solve for. So I know my initial conditions before, right? So I know this one, I know this one. And my temperature average after, it's going to be the same as well, right? So the only one that is going to be, there's going to be changing is this one. But this one, it's like, okay, yes, because this one is affecting this too. So what I'm going to do is I'm going to reorganize everything here. So my temperature of my steam generator after is going to be equal to my temperature average after. This is going to be minus temperature average before minus temperature steam generator before, which are my original values, over the 0.95, because this one I just need to bring it down, right? Put it in here. And this one I need to bring it to the other side. So that's why I end up having this formula right here, rearranging everything. So if I plug numbers in, I'm gonna get that my temperature of my steam generator after is gonna be approximately 532 Fahrenheit. And if I check my steam table to check the saturated pressure under that at that temperature, I'm gonna get that the pressure of the steam is gonna be 900 psia. That's gonna give me the answer delta. So it's kind of like a little confusing, but as long as you know that you're gonna use this are your initial values, you're gonna just use them on one side of the equation. If it says that you have your tubes plugged in your steam generator, that means that only 95% of your steam generator after is gonna be functional. The average temperature of the RCAs, it says that it remains the same. That's why we are using the same temperature here. The only one that we need to get is this part that we don't know, right? Because that's the one that changes. And I think for that one, that will be it. I'm trying to see if there are other questions that might be a little complicated to solve. But I think everything else is just very straightforward. So you're gonna have some other questions about tank of the mass, calculating the tank of the mass. That's like very straightforward questions, and we have the formulas at the beginning of the video. There are gonna be other questions where you have to calculate the volumetric flow rate. So you already have the formula for volumetric flow rate, and remember what comes in comes out. You just have to rearrange stuff in it. It's very, very straightforward. So I think that's gonna be it for them. And there's gonna be only like a question where you have to kind of like calculate the efficiency. So let's go over that one. There's gonna be question P7679. P7679. This one. So this one says dry saturated steam enters the turbine at 1000 psia. Okay, we're entering the turbine at this pressure, and we are exiting the turbine at this pressure because we are entering the condenser, so that makes sense. The efficiency of the turbine is 85%, Now, what's the question? So the question is, what is the approximate specific work output of the turbine? Okay, this is the formula that we're going to use, and it's given. So this is efficiency equal enthalpy. We're going to use enthalpy of steam minus enthalpy of the exhaust. This is real. And this is ideal. Okay? Because we are giving that information already. So what we have to do is, let's go to our steam tables. If we go to our steam tables and we look for 1000 psia, 1000 psia, which is not going to be directly there, but remember it says dry saturated steam enters the turbine at 1000 psia. So that's Hg at 1000 psia. So we can go to a different page on the steam table. I will go to page number 20. Page number 20, saturated steam is giving me 1192.6 BTU pound mass, right? And that's gonna be for the steam. So I got that one, okay? So now what else is giving me? So I have this 2 psia there. Okay, now let's go back on the pages on the steam table. Do I have 82? No, but I can go to the temperature and try to find something close to that. So if I go to page 6 and I look on absolute pressure, instead of looking for the temperature, I look for absolute pressure, I can see that there's a pressure of 1.9985, which is very close to 2. So I'm going to use that one, right? I'm going to use that one, and since I know that what's exiting on my turbine, it's already condensed, right? So I'm going to go to so I know is 2. So let's take a look at this. Okay, so on this one, I go there and I found that my HF is 95 or 93. It's 1000 or 1115.7. So at 2 psia, I have 1115.7. So then I go to my steam table and I look at that and I'm like, okay, I'm finding something else here. I'm looking at HF of 93 and 95, but I have like a feeling that something is off, right? So one of the things that I do and that I need to do, and that I need to use in here, that is very important, is to use my Mollier diagram. So I cannot show the Mollier diagram, but I have my Mollier diagram here. So what I need to do is to go to my Mollier diagram and go to where I have my 1000 psia and my 1192.6. So I have to go to that point, right? I have to go to that point, and then I have to go all the way down to where I cross the mark on 2 psia. So I go all the way down, and where I cross that mark, I'm gonna get around 850, maybe 800. I get 850 approximately, right? That's kind of like how I'm reading in here in my. Yeah, that's how much I'm seeing here. Oh, because I'm at 900, that's why. So no, it's gonna be around 805 approximately. So I just have to go down. So let me explain this. So I have my thing here, right? So I have to go to the point where I have the 900. I'm sorry, not 900. The 1000 psia saturated light, and that's gonna give me the 1192 black, right? I'm saturated. Then I have to go all the way down to where I cross, and I'm just gonna make them more steep so it makes more sense. Let's assume this is my 2 psia line. So I have to go all the way down on my Mollier diagram, and when I reach the 2, I need to go here and read that number, right? And that number is gonna be about 805 BTU over pound mass. Because if I go to my steam table to 2 psia, I'm gonna get a different number. So on this one, we're talking about what's happening in the turbine, right? So that's why I have to use my Mollier diagram here. It's very, very important. So here, start getting used to it, like comparing like the information that you get from your Mollier diagram and your steam table. Okay? So now that I get that information, that I know how to get, I'm just gonna erase this. I start plugging things in here, right? So I have all of this one. So now I know what numbers to type in correctly. So because I need to get this part. This is the enthalpy that I need to get because I need to get my real enthalpy from this efficiency, right? If I'm using efficiency, I need to get my real enthalpy. So I plug things in. So what I'm gonna get is approximately 863. Okay. Do I see that in here? No. I don't see it in here because that's not my answer yet. It's not asking me about my enthalpy. It's asking me about the work output. And this is just one step. So now, to calculate the work of the turbine, I use the steam, the enthalpy of the steam minus my real enthalpy. So I just plug things in here, which is going to be 1192.6 minus, calculate 863. That's going to be about 329 BTU per pound mass. Here we use again this part, but this is an important one that we really need to calculate. We cannot just go directly to here because we are giving the efficiency of the turbine. That's why we need to use this extra step above to calculate that one. So that gives me the answer to be alpha. And I know, like, sometimes you're gonna be like, oh, I'm confused, what's going on? Well, that's the reason why we need to look not only our steam tables, we need to have to develop that intuition and start looking at the Mollier diagram a little bit more, right? So now there's another problem in which I created, in which I, got my formula that I memorized. So let's take a look because you might not have it, so I want you to have it. So it's P4939. P4939. Because this one they give you Bernoulli's equation all the way through, and you have Bernoulli's equation in your exam. Like they give you some formula sheet on your exam, and they give you the whole Bernoulli. You don't want that. So what I do is I just memorize this, and I know this one works for this question. It doesn't work for another question. No, I think it only works for this question and this question only. So yeah, I use this one. And there's another question that is gonna be similar, so I'm just gonna give you the shortcut for this one. This one I memorized it, and it's not very hard. But let's take a look at question P4939. So water enters an ideal convergent divergent nozzle for the following parameters, and they're giving me the parameters. They're giving me pressure, temperature, velocity, and also they give me the velocity of the water at the throat of the nozzle. Okay. And I have almost everything. So this is my velocity 1. This is my velocity 2. And what else? So they give me pressure, they give me temperature. Now the formula. They're gonna give you Bernoulli's, but this is the formula that I use. So they're giving me the pressure 1. So they are telling me, okay, what's the pressure of the water at the throat of the nozzle, the exit pressure. You have pressure in, pressure out. So what's my exit pressure? So this is what I use. I use pressure 2 equal to pressure 1 times specific volume times 144, which is a conversion factor, minus, and some people are like, oh, I have to memorize that. I'd rather derive it, but honestly, to me, it works marbles just doing it like this. Because at the bottom, I use this one. I know that I'm going to use that part. So I try to memorize it. So if I plug everything in here, because I already have velocity 1, velocity 2, these ones are conversion factors. I have pressure 1. I only need to get my specific volume. That's the only thing that I need to get. So for my specific volume, I just need to get the specific volume at my temperature, 102. So if I go to my steam tables, and I go and get my specific volume at 102, and let's look for it. Temperature 102, the specific volume is going to be 0.016138, right? Because it's here. 0.01, C102, 0.016138. So that's gonna be my specific volume. It's gonna be so that's what I'm gonna use for this one. So I just plug that in here, and I basically have everything to get my pressure in it. Everything is given. So if I get my pressure at 300, I can take a look at my pressure at 300. That's a very high pressure, honestly. So the specific volume is gonna be way lower. So we know that what we have in my nozzle, it's gonna be, because I'm using the pressure already here. So this is the pressure that I'm using, like P1. So that's why for my specific volume, I'm using the temperature, and I also know it's a fluid, right? So that's why I'm using that. So I hope that helps, and that's the formula that you'll use for this one. You just plug everything in. I memorize it. So and just remember this part is the same, and I will get this answer. There's another one that it also uses Bernoulli's, and I'm just gonna give you the formula for that one. It's question P5239. P5239. For this one, it's gonna be a little different. This is the formula that I use for this one, because it comes a little bit confusing. It's a little bit confusing, but basically it's velocity 2 minus velocity 1 over 64.4, which is the conversion factor, plus, and here we use the enthalpy. Enthalpy 1 minus enthalpy 2 equals 0. So that's the formula. So here you got the velocities, right? You have velocity 1, you have velocity 2, and also you are giving a pressure, right? So you're giving a pressure. So if you go and take a look at the pressure for 850 psia, here are you, 850 psia, and you look at the specific volume here for the steam in this case. It's gonna be 1197.8. It's gonna be 1197.8, right? At 850. And in this one, how do you know? Because you're telling like convert enthalpy to kinetic energy. So here it's already telling you that you have to use enthalpy. So that's how I know I don't need to use the other formula, right? So I need to use the enthalpy one. And I just need to solve for enthalpy in here. So I just move it outside, solve for everything, and the answer that I will get is going to be closer to Charlie in this one. So you can do that one. There's another one. This one I will give you the formula as well. It's going to be P6139. 6139? Why? I don't have it in here. Wow, it's not in here. Well, I wanted it to help you. Okay, this one seems like it's not in here. 6139? No? Wow. Okay, I hope you don't get it. I really hope so. So, and I think that's gonna be about it, like from all the difficult questions that you're gonna have. So I think I will leave it to that, and those are the formulas that you're gonna use. And I think that's gonna be it for section 183.003. If you have like a specific questions, just let me know, like, and I can try to upload a video just for that specific question. And I hope this helps. Thank you.